we go. Okay, I'm just going to read Daniel's bio here. Welcome back to BUsec, everybody. Daniel Wichs is an associate professor of computer science at Northeastern University. He works on all aspects of modern cryptography, including its theoretical foundations and its applications to information security. His most recent research relates to the cryptographic challenges involved in outsourcing data and computation to the cloud. So, Daniel, tell us about all of those things.
So, okay, I'll actually tell you about none of those things. I'll tell you about something, a different topic. So I'll tell you about incompressible encodings, which is, there's some application to the cloud, but it's not the main application. So this is a joint work with Tal Moran, and it's a work that appeared at this past crypto. So let me start with a question for the talk. So how much space would it take to store all of Wikipedia? So it turns out that you can actually download the Wikipedia data for offline use if you want to look up articles in Wikipedia when you're not connected to the internet. And depending on the version you get, some reasonable version of it takes about 50 gigabytes. You can download it and store it on your computer. It's about 50 gigabytes. So as you expect, you know, Wikipedia has a lot of data, so it's quite large. But there's a different way of storing Wikipedia, which is just to store the link, www.wikipedia.org. That only takes 17 bytes. And as long as you have a connection to the internet that's good enough, it's just as good as storing the Wikipedia data. You can access it whenever you need. And so the point I'm trying to make is that when it comes to some public data like Wikipedia, even though the data could be huge, because it's public, you can essentially store it for free just by storing the link. And the question for this talk is, can we take some public data like Wikipedia and make it incompressible? So can we come up with a representation of the Wikipedia data that would require like the full 50 gigabytes to store, even for someone who has an internet connection and has access to the original Wikipedia data for free, doesn't pay for storing the Wikipedia data itself. And so that's the question of incompressible encodings. So I'm going to tell you what they are and then how to construct them. And all the way at the end, I'll talk about some applications. Why do we actually care about this? Why they're useful? It turns out that there's a couple of really nice applications of these things. So here's an incompressible encoding. Let me get straight to it. So it just consists of an encoding algorithm and a decoding algorithm. These are public algorithms. There's no secret keys or anything. Anybody can run them. And the encoding algorithm takes some underlying data M, let's say the Wikipedia data, and encodes it in some probabilistic way. So it's a randomized algorithm, and it outputs a codeword C. And so the way I chose to draw it or represent it here, it's I made it like a grainy version of the Wikipedia logo, just to indicate that there's some randomness dispersed throughout this codeword or incorporated into the codeword. But this codeword actually serves as just an alternate representation of the underlying data, and anybody can come and decode it and recover the data whenever they want. So storing the codeword is just as good as storing the data. You don't need any secret keys. Anybody can come and decode it and get the data out. So we can just think of it as some alternate representation of, let's say, the Wikipedia data. And well, the main functionality property we want from this coding is just correctness. So if I encode some data M and decode it, I get back the original data M. This should hold with probability 1 over the randomness of the encoding process. I should mention that you might also want to get local decodability, which is that if you want to just read one article on Wikipedia or look up one small location in the data, then you should be able to do so without having to read the entire codeword and decode it all. You should be able to just read a few bits of the codeword to recover, let's say, 1 bit of the original data. And it turns out that the constructions we have get this. So it's easy, and in fact, there's even you can even achieve this somewhat generically for incompressible encodings. So for the talk, I'll mostly ignore this aspect of local decodability. The questions are interesting even without it, but if you want it, you can have it as well. So let's talk about the security property that we want. And here I want to consider an adversary that knows the data M. for free. So think about it like he has access to the internet and knows what the Wikipedia data is. The goal of the adversary is to compress the code word down to some smaller value, which is good enough to recover the code word. So the adversary consists of two procedures, a compression procedure, which gets as input the code word and output some smaller value that we'll call the compressed value W, and a decompression procedure that takes the compressed value W and uses it to recover the code word. And let me put some parameters. I'll call the code word size alpha, and the value of the compressed value W that the adversary outputs, I'll call that beta. And essentially, the adversary's goal is to make beta much smaller than alpha, so to compress the code word down to some much smaller size. And the security property says that this should not be possible. So we'll say that for every message M, for any worst case choice of the data, notice here the data has no entropy. It's known to the adversary. It can be hard coded as part of the adversary. So we're not assuming an entropy on the data M. For all messages M and all efficient adversaries that consist of these compression decompression algorithms, the probability that if you encode the data M via this probabilistic encoding procedure and give the code word to the compression algorithm, and then you decompress the output of the compression algorithm, you get back the original code word, should be negligible. So this compression decompression procedure should not succeed. Okay, at least for all compression procedures that output in most beta bits, where beta is some parameter of the system. Okay, so this says that the code word cannot be compressed below beta bits or 2 beta bits. And so there's two parameters here. There's the size of the code word alpha and the size of the code word of the compressed value W, or how much the adversary can compress. And ideally, we want both of these to be very close to the message size. So that says that when I encode the Wikipedia data or some data M, I don't have much overhead. My code word is almost as big, essentially as big as the data itself. And also the adversary cannot compress it essentially at all. If he wants to have some way of remembering the code word, he has to store almost the entire code word, almost all alphabets. So this is the goal. This is the goal of incompressible encodings. Any questions?
I'm looking for like a practical motivation. It's a well-defined mathematical question. They're very interesting, but what will be the setting in which I want to use it?
Yeah, so I have two applications. Unfortunately, I moved them to the end of the talk. I wanted to get to them earlier. I agree, it'd be nice to see them.
Okay,
yeah, we'll get to them. There'll be two nice applications of this.
Okay.
Yeah, so looking forward, for example, one application will be I'll want to use some encoding of some like public data, let's say Wikipedia, as a secret key for a crypto system, and I'll want it to be incompressible to make sure that it's hard to let's say for an adversary to like steal this secret key of my computer. But we'll get to it. So
Okay.
let me get to it
Sure. Okay.
when the time comes. Okay. So let me just mention that there is a trivial way to solve this problem, but not with the parameters we want. So here's a trivial incompressible encoding. To encode the message M, I'm just going to set my code word to consist of the message M and some additional extra random bits that I'm going to append to it. So I'm going to append some extra red, the red portion of this code word will just be random bits. And this ensures, because the red part of the code word, these random bits are truly random, those cannot be compressed. So you know that the adversary has to at least store the red part of the code word. But because he knows the data M for free, he has access to that, let's say on the internet, he doesn't have to store the blue part. So he can compress the code word quite a bit. He just needs to store the red part, not the blue part. So this achieves beta, which is alpha, the code word size minus the data size. Essentially, the incompressibility parameter is just the red part, and that's not what we want. That's not good enough for what we want. But unfortunately, it turns out this is as good as you can do information theoretically. This is the best you can do information theoretically. So what we want is something better, which we'll need computation assumptions for. We'll essentially want to take this randomness, the red part that was that we had before, and somehow disperse it throughout the code word in some clever way, such that it's hard to for an adversary to separate out the randomness, the red part and the blue part. And so we want to make sure that essentially the adversary cannot, even though the blue part is something he knows for free, he cannot compress down this this code word, which is the red part, the randomness, and the data somehow cleverly dispersed and combined together. He cannot separate them out and just store the red part, which is small, and rely on the fact that he has the blue part for free. He has to somehow store the entire code word to be able to later recover it. So here we want the code word size to be almost as big, not much bigger than the message size, just 1 plus little 1 times the message size. So let's say the overhead is less than like 1%, and beta also to be 1 minus little 1 of the message size. So you cannot even save 1% in storage when you want to store this code word.
Quick question. Does the adversary have access to the randomness used by the encoding procedure, or can the encoding procedure have secret randomness?
No, it's actually very important that the encoding procedure has secret randomness.
Okay.
Otherwise, the adversary could, at least if the encoding procedure used a small amount of randomness, the adversary could just store the randomness, and use that to recover the code word.
Okay.
Yeah. Okay, so this is these are the parameters we want. And with these parameters, I just want to make a point. So if you look at the code word, it has very little real entropy because it's only slightly bigger than the message size. And so there's and the message has no entropy, it's worst case. So there's no space to put any too much real randomness into the code word. So it has very little real entropy. Moreover, the code word even has very little pseudo-entropy, at least if we talk about help pseudo-entropy. So help pseudo-entropy means it's indistinguishable from some random variable that has a lot of entropy. And this is true because if you take something with a lot of entropy, it's unlikely to decode to the message m. Right? If I took, it's unlikely if I took a random value that had a lot of entropy to decode to m, whereas the code word here, the output of the encoding procedure on a message m always decodes to the correct message m. So I can in fact distinguish this code word from any random variable that has a lot of entropy just by testing whether it decodes to the message m that was supposed to be encoded. So this code word has little real entropy, even very little computational entropy. But nevertheless, I want it to be essentially as incompressible as a uniformly random value would be. So there's this tension that the code word has some interesting structure, decodes the message. Anybody can check for this structure, but nevertheless, it has a high degree of incompressibility, and that's what makes this problem interesting. So I want to mention one more property of incompressible encodings called composability. And the property I want is that, let's say I encode many different messages, or maybe the same message many times, and I get many different code words. Is it possible to compress all the code words together in a better way than compressing each one separately? So let's say I know that the incompressible encoding cannot be compressed below beta bits. But if I take n code words, can I ensure they cannot be compressed below n times beta bits? And it's actually an interesting question. So if we were in the information theoretic setting, then this always holds, essentially because Shannon entropy of independent random variables just adds up. So if you cannot compress something information theoretically below beta bits, if you take n independent copies of such a random variable, you cannot compress below n beta bits. But computationally, it's unclear if this always holds. In fact, it seems it's very hard to do a reduction. It seems like you won't be able to do like a black box reduction that if an adversary can take n code words and compress them below n beta bits, he could compress one code word below beta bits. And I suspect there should be counterexamples, although I don't know of any under even strong assumptions. So it's an interesting question to come with counterexamples.
Is this the same as local decodability?
No. So local decodability is a functionality.
Local decodability?
Say it again?
Does it imply local decodability?
No, this is unrelated. So local decodability is a functionality property. It says that I can decode a bit of the message by only reading a few bits of the code word. This says this is a security property. It says that if I cannot compress many code words below what it would take to compress each one separately.
Sure, but let's say I had a composable, incompressible encoding scheme for like small message space. Then I could just compose those encodings to get an encoding for the large message space, and that would be still an incompressible encoding and also locally decodable.
Good. That's right. Yeah. So that's one way to get this almost locality almost generically.
If you have composability.
If you have composability. That's right. Good point. Okay.
Just a question. Sorry. So just to make sure, so your security requirement is that it should be impossible to get the entire code, the entire word, entire M, right? So it's like one witness. It's okay if I can get half M, but not all M. As far as
not M, the code word. So the message you know for free. It's the code word you're trying to.
Okay. Right. Okay.
But yes, the goal is you should not be able to get in the entire code word. You might be able to get half of it.
Okay. Yeah.
And in fact, I'm gonna let you store. I'm gonna let you store like 1 minus little 1 fraction of the code word. It's the property we want is even if you store 1 minus little 1 fraction of the code word, you cannot get like the entire code. You cannot get the entire
Right.
code word.
Right. Okay. Yeah. So yeah. So it's interesting. Yeah. So yeah, this composition is I can see why it's hard. Interesting.
So we're gonna, because it's unclear and unlikely that it holds generically, that all incompressible encodings are composable, we're gonna just define it as an additional property that we want from our incompressible encodings. Okay, so let me say a little about this notion of incompressible encodings, its history, how it appeared in prior work and what our results are about. So there's a prior work of Damgård, Ganesh and Orlandi from Crypto 2019 that essentially defined this notion or a small variant of it. And they defined it as a tool to build a bigger or larger cryptographic scheme called proofs of replicated storage. And I'll tell you a little bit about those later on in the talk. But they mostly thought of these incompressible encodings as a building block for this bigger crypto systems. But in this context, they constructed incompressible encodings, although with like several caveats. So first of all, they relied on the random oracle model. They didn't get a construction of the standard model. The encoding time to encode a message was quadratic in the message length. And if you want to use this for encoding large data like Wikipedia, if you want to run in quadratic time in like the size of Wikipedia, that's really, really impractical. They only managed to get bounded composition, so it was composable for like some a priori bound on the number of different code words you'll take, but you needed to know this bound ahead of time and actual efficiency degraded in the bound. And lastly, it turned out when we were thinking about this problem, we realized that the proof in their paper was somewhat flawed or at best incomplete. It assumed some restriction on how the adversary acts, and it didn't carry over to general adversaries. And this was actually also noticed by a concurrent work by Gargle and Waters, and they managed to fix this. They gave a new proof for the scheme of Damgård, Ganesh and Orlandi. It was actually quite non-trivial. The proof of this construction from that work is quite subtle and difficult proof to get right. So in our work, we actually take a different approach. We give a different construction of incompressible encodings with several benefits. So we get security even in the common reference string model rather than random oracle model. So we get rid of random oracles. The encoding time is linear. And we have a very simple proof. It'll be like 1 or 2 slides that I'll show you in a little bit. I'll tell you more about the comparison between these 2 works and some of these, some variants of like what kind of incompressible encodings they achieve. We also give some lower bounds and negative results that essentially show that some aspects of our constructions are optimal. For example, we need to rely on a CRS. We cannot do it in the plain model. And lastly, we give a new application to Biki cryptography. And so I'll talk about, so first I'll tell you about the constructions, and then I'll tell you about the applications, both to proofs of replicated storage and to Biki cryptography. But before I do that, let me just give you the comparison in a little more detail between our work and the previous works. So in the prior work, they constructed this object, these incompressible encodings, in actually the ideal permutation model, which is a little stronger than random oracle model, plus using general trapdoor permutations like RSA. They got bounded composition, so you needed to know some bound on the number of code words that the adversary will try to compress, and the scheme depended on this bound. So I'll call this parameter Q, the number of compositions. And the complexity of their construction was depended on Q, and was O of Q times M squared. So it depended both on the number of compositions, but maybe more importantly, it was quadratic in the message size. And as I said before, this original work had a flawed proof. This was fixed by Gargle and Waters. They also showed how to remove the ideal permutation and just get a construction of the random oracle model. So for our work, we managed to get a construction that that's in the common random string model. So we remove the random oracles, but we do this at a cost. We don't rely on general trapdoor permutations. We rely on something slightly different and incomparable. So for example, we get constructions under either the learning with errors assumption or decision composite residuosity assumption. So the good news is, on the positive side, we get a construction under learning with errors where we don't have trapdoor permutations under LWE. So we actually do something a little better in that sense. But on the other hand, I don't know how to get a construction from plain RSA. We need this decision composite residuosity. It's maybe a little less efficient than RSA trapdoor permutation. We get construction with unbounded composition. You can compose as many code words as you want, but you do need a fresh CRS for each composition. So we're in this common reference string model, common random string model. You need a fresh common random string for each encoding. And lastly, the complexity of the construction is just linear in the message size rather than quadratic. But one downside of this construction is that you only get selective security where the message has to be chosen before the adversary has to choose the message before the CRS is chosen. It cannot depend adaptively on the CRS. And the CRS is very long. It's as long as the message size. So we need the common random string. Let's say if you're encoding Wikipedia, has to be as big as Wikipedia. And not surprisingly, you can get rid of all these restrictions by moving to the random oracle model. So in the random oracle model, you get rid of the CRS altogether. You don't need a fresh CRS per use, and you get even adaptive security. There's no restriction on selective security. So you get essentially remove all the negative aspects. So in relation to the previous work, the main thing is in the random oracle model, we get unbounded composition and we get complexity just linear in the message size. Okay, and so I'm not going to talk about this last transformation to the random oracle model, but essentially the way you do this, if you have a scheme in the CRS model, you can just use the random oracle to select the CRS. And in fact, you can choose a small seed for the random oracle that you append to the code word at encoding time to ensure you get a fresh CRS for every time you encode. And therefore, you don't have an issue of selective security or adaptive security because it's as though you're choosing a fresh CRS for each code word. And the adversary cannot predict the CRS ahead of time.
Daniel, sorry for interrupting, but isn't it sounds to me almost trivial in the random oracle model, right? You know, you just pick an encoded, you want to encode it in some length, you just pick a random word of some length and you run it through the random oracle, assume it's random oracle from 0, 1 star to the length of messages, and then you just output the random oracle. You output the preimage of the random oracle together with the XOR of the image in the message or something.
So actually, it's a great. So I'm not trying to totally understand your proposal, but it's a big open problem to do this in the random oracle model without, let's say, trapdoor permutations or public key assumptions. So both constructions need more. But I think the problem with what you were saying is, so first of all, how do you invert the random oracle as an honest user, right? It has to be efficient.
Oh, you don't. Well, you have the encoding, right? You have the encoding.
So maybe I didn't understand the suggestion.
Okay, never mind. Let's not waste time.
Okay.
Yeah, obviously, there's something wrong. I need to understand. Okay, sorry.
Yeah. Sure. So maybe after you see the construction, maybe you can it'll be clear, and you can ask your question again. Let me just mention we also have two black box separations or negative results. So we show that you cannot get a construction in the plain model. You really need common random strings. And even in the CRS model, the common random string has to be long as the message, and you can only get selective security. So the fact that we didn't get adaptive was sort of inherent. You cannot do this in the CRS model. At least if you want to have a black box security proof under some simple single stage game-based assumption, some standard assumption like DDH or LWE or RSA, etc. So that in some sense shows that the constructions we have are in some sense optimal. So let me now show you the construction. It's actually quite simple. I'll give you the construction and the proof, and then I'll get to the applications. Okay, so I'm going to give you a construction, but I'm going to make it, I'll give you a slightly simplified construction that assumes that we have a really nice object called the Lossy trapdoor permutation. And so looking ahead, we don't actually have something as nice as the Lossy trapdoor permutations that we need for this construction. We have something that's similar, but not quite there. And we'll need to adapt the construction, or we'll need to adapt a little bit to handle this less nice primitive. But for simplicity, for now, let's just assume we have this really nice object called the Lossy trapdoor permutation. I'll tell you what that is. So Lossy trapdoor permutation is just a family of functions, f, that's keyed by some public key pk, and it maps n bits to n bits. So the domain and the range are both n bits. And the property is essentially the same as Lossy trapdoor functions, if you know what they are, except that it's also a permutation. The range is the same as the domain. So we can sample the public key in one of two indistinguishable modes. In injective mode, the public key, the function fpk is actually injective. It's a permutation over 0, 1 to the n. And the public key comes with some, you can choose it along with a trapdoor that allows you to invert the permutation efficiently. On the other hand, you can sample the public key in lossy mode, and nobody can tell the difference between which of the two modes the public key was sampled in. And in lossy mode, if you look at the function fpk, it's very much not injective. In fact, the image of the function is much smaller than the range. So it maps the entire domain 0, 1 to the n to some very few to very few possible outputs. And what that means is that if I take a random x and I give you fpk of x, then this loses a lot of information about x. I'm actually not giving you too much information about what x was. Okay, whereas in injective mode, if I give you fpk of x, I give you all the information about x. Okay. All right, so we're going to use these lossy trapdoor permutations to construct incompressible encodings. And the construction is very simple.
Hey, Daniel, could I ask the basic question? Are there constructions of say pseudorandom permutations from LWE? I can't think of one off the top of my head, but I'm sure I just don't know. Like I wouldn't know.
Oh, so, well, you can get pseudorandom permutations from one-way functions, like.
Okay, yeah, that's fair.
Yeah. So pseudorandom permutations are a mini crypt primitive. Lossy trapdoor permutations are cryptomania primitive.
Yeah, I guess I'm just thinking of like a more direct construction. But whatever, I don't know how to define that, so forget it.
Okay. So here's the construction. So the CRS for this construction is just going to consist of a bunch of random values yi, where you can think of these yi's as the outputs as being in the range of the pseudorandom permutation. I mean, the range and the domain are same; they're both 0, 1 to the n, but think of them as being in the range of the pseudorandom permutation. And to encode a message m, where I'm thinking of the message m as consisting of L blocks, each of n bits, each block consisting of n bits. I'm just going to do the following. I'm just going to sample a public key and a trapdoor for the lossy trapdoor permutation in injective mode. So this public key is in injective mode. And then I'm going to use the trapdoor to invert the permutation on the blocks mi XOR yi. So I'm taking the message that I'm encoding, XORing it with the component in the CRS, and inverting. Okay, and the code word just consists of the public key and these pre-images x1 up to xl. So so I want to mention the only randomness in the encoding procedure comes from the choice of the public key and the trapdoor for the lossy trapdoor permutation. That's the only choice of randomness. Once you fix the public key, the rest of it is deterministic. As you can see, the code word is not much bigger than the message. Actually, it's exactly as big as the message, except for the public key. So it has some small additive overhead. Okay, and lastly, it's very easy to decode this code word. I'm just going to apply the permutation in the forward direction and XOR with the values in the CRS to recover the message. And you can also see I can locally decode by just applying this on the block, doing this for the ith block, where if I just want to decode the ith block, I can just do this for the ith block without looking at the rest of the code word. Okay, I want to mention one more thing. So when I encode, I sample a public key and a trapdoor for the lossy trapdoor permutation. You can think of the trapdoor as being part of the secret coins of the encoding procedure, but I throw the trapdoor out essentially after I'm finished encoding. So the code word does not have the trapdoor; it just has the public key and x1 xl. So the adversary does not have the trapdoor for this permutation. Okay. So that's the main idea, and intuitively this ensures that if the adversary wants to remember the pre-image of yi, so the adversary knows yi's, he knows the mi's, he knows the message, and he's trying to compress the code word. And somehow this ensures that if the adversary wants to remember the pre-image xi, he cannot compute it himself because he doesn't have the trapdoor. He has to remember the entire pre-image xi, even though he has both yi and mi. He cannot compress xi without storing it. That's the high-level idea. But let me actually give you the proof of security. So the adversary sees the common reference string, the CRS, so all the yi's, and he sees a code word, the encoding of some particular message m. And his goal is to compress the code word given the CRS. So in real life, let's look at this distribution of what the adversary sees. So in real life, the public key is sampled in injective mode. The yi's and the CRS are uniformly random, and the xi's are these pre-images, inverting the trapdoor permutation of mi XOR yi. And you can think of yi and xi, if you look at it, each one of them is individually uniformly random, but if I get both of them together, they define the message. I can recover the message. So somehow yi and xi, you can think of it as just some sort of information theoretic secret sharing of the message mi. Individually, each one is random, but if I get both of them, they define the message. So as my first step, I'm going to switch this distribution to the following. I'm going to choose xi, the values in the code word uniformly random, and then I'm going to define the yi's in the CRS in the right way, so that the yi and the xi are still a secret chunk of the message. So I'm just going to set yi to be fpk of xi, xor mi. So if you look at this distribution, nothing changed. It's exactly identical to the real world, except that in the real world, we couldn't have done this. We couldn't have chosen the y's this way because we didn't know the CRS should be uniformly random. It should be independent of the message. So in the real world, the CRS is random and the code word depends on the message. Here, I switched it to have the code word random, and then I'm fixing the CRS to depend the message in the right way.
And this is where selective security is coming in.
And that's right. And this is exactly where we rely on the fact that I'm only proving selective security, that I know what the message is in the security game at the time where I give the CRS up, where the adversary sees the CRS. So this distribution is identical, but now I'm going to set the public key to be lossy. And notice that in the middle distribution, I'm not using the trapdoor anywhere. I'm not computing FPK inverse. And since I'm not using the trapdoor anyway, you can distinguish whether the public key is injective or lossy by the secure of the lossy trapdoor permutation. But now that I've done that, now that I've made the public key lossy, if you look at it, the xi's in the code word are actually uniformly random. They have a lot of entropy. The CRS reveals some information about them, fpk of xi, but not too much. So actually, even if you have the CRS and even if you know the message, the xi's have a lot of statistical entropy in this game. So the code word has real entropy in this game, given the CRS, and therefore it's information theoretically incompressible, given the CRS in this last distribution. Therefore, so in this distribution, the adversary, even an unbounded adversary, could not compress the code word. And therefore, in the original distribution, the adversary also cannot compress the code word, otherwise he could distinguish. That's the entire proof. So I just want to say one more time what we did here. In real life, all the information about the message is contained in the code word, and the CRS is just random. But somehow through these two steps, through these two hybrid steps, we moved the information about the message into the CRS and had the code word actually have real entropy. And then we argue that even given the CRS, it's impossible to compress the code word. So somehow in real life, the information about the message can be contained in the CRS, it just contained the code word, but we switched it to a hybrid world, or we did a sequence of hybrid where we moved the information about the message to the CRS and the code word was really random, had real entropy. So that's pretty much the entire proof. I want to talk a little bit about the instantiation. So unfortunately, it turns out we don't have lossy trapdoor permutations that are this nice. In fact, if you think about lossy trapdoor functions, which is an area that's received a lot of study, there's a lot of construction of lossy trapdoor functions. So they're injective, but they're not surjective. Like the constructions we have from DDH or LWE, or almost all of the constructions we have are not surjective. And that's really bad. In the construction we had, it's important that we take random values in the CRS and are able to invert them for correctness. Whereas for most lossy trapdoor functions, if I take a random value in the range, it's unlikely to have a pre-image. It's not, because it's not surjective, it doesn't have anything mapping to it. So we cannot rely on most of the lossy trapdoor functions in the literatures. And also, there's an exception. So we have a lossy trapdoor permutation that actually is surjective based on decision composite residuosity, but it doesn't have a nice domain like 0, 1 to the n. The domain is like z and star, where n is some RSA modulus. Yeah. So we have to handle this, and essentially we showed that this we can relax the notion of lossy trapdoor permutations while still making the above construction work. So it turns out we don't actually need the function to be injective. So we define something called surjective lossy functions, where in one mode, in surjective mode, every value in the image has very few pre-images mapping to it. So essentially, the functions may be a little bit lossy because there's like more pre-images than there are values. The domain is bigger than the image size. But in surjective mode, it's not very lossy. Every value in the image has very few values mapping to it. And in lossy mode, there's just some small a subset of the image that everything maps to. So in lossy mode, you're really lossy. In surjective mode, you're not injective, but you're at least surjective. And we show how to construct this from decision composite residuosity and LWE. And essentially, it's good enough for the construction with like small, minor, essentially cosmetic modifications to make this work. But the idea is exactly the same as what I showed you on the last slide. I want to mention that this relaxation to surjective is important because, for example, I don't know how to build even trapdoor permutations, forget lossy, just trapdoor permutations under LWE or under nice post-quantum assumptions. So here, by relaxing it to surjective lossy functions rather than lossy trapdoor permutations, we can get constructions from LWE and other assumptions that we didn't know imply trapdoor permutations. Okay, so that's all I want to say about the instantiation. Any questions about the construction?
Can you flash the construction one more time? I just want
Sure.
Why is there? I see. Okay. Sorry, I was just. It makes sense. Great. Sorry, I confused myself. Okay, good.
Good. I guess I should say like maybe a little intuition about why it seems like trapdoor permutations are inherent. Why I don't know how to do it from, you know, maybe also to answer Ron's question earlier about can we just use like random oracle or maybe an ideal permutation? What about if we replace FBK with an ideal permutation? Could you do that? And there the problem is if it was just an ideal permutation, well, I guess there would be, you know, be trivially breakable because you could also compute it in the forward direction. So essentially, if you were able to, if you have the MIs and the YIs, the message and the CRS, you would be able to compute the code word on your own without storing any data, right? You would just remember the public key and then, let's say, or you know, compute in the forward direction. So it seems somehow important that we have that the encoding procedure does something that the decoding, that the adversary cannot invert or replicate. So there's some notion of a trapdoor permutation that seems to be needed or useful, but of course I don't know how to prove that.
Daniel, I do have a question.
Mm-hmm.
Is there a reason that if you go back to slide,
yeah,
is there a reason why the the XOR happens inside of F and not outside? Like I could have chosen XI to be F inverse of Y XOR M. Y F inverse of Y XOR with M. Is there a reason not to go that way? Just I don't see a good difference between those two constructions.
Good question.
You could still decode. You would apply F to X XOR Y, I think.
No, hold on. Oh, F inverse of Y XOR M. Actually, no, I don't know how to decode, right?
No, you take you XOR X and Y, and then you apply F to it.
No, but you have F of Y. Yeah, I think it's exactly because I think you answered your question. It's exactly because I don't know how to decode for that construction. Right, because I get F of Y XOR M. I don't know M when I'm decoding, right? That's the whole point. I want to recover.
Oh, sorry, I don't know what I said before. F. What if you take F inverse of M, and then
well, the problem is M is not random, so F inverse of M has no security.
Okay. Got it. Okay, thanks.
Okay. Good. I see there might be some tech chat messages. If there are any questions, let me know.
So no, I wrote my naive suggestion on the chat, but I don't want to stop you. Maybe.
So
maybe we'll come back to it
let's do it at the end of the talk.
Yeah, let's do it in the
Yeah.
end. Yeah, let's do it in the end. Yeah.
Sounds great.
Sorry, just another quick question. Are you going to talk about why CRS seems to be inherent, or is that outside of the scope of the talk you have?
I wasn't planning on talking about that. I'll just mention we have it's a black box separation result that essentially says that if you had a construction without CRS, there's no proof of security that would, you would not be able to get a proof of security that treats the adversary as a black box and proves security under some nice assumption. And I should mention, I guess, let me just mention about these black box separations. So the reason we're able to get such black box separations is because the security game for incompressible encodings has a slightly strange format. It's a multi-stage game where the adversary has two parts, the compression algorithm and the decompression algorithm, that don't talk to each other. And we're able to show that at least without a CRS, you cannot prove this type of security from any assumption that talks about just a single stage adversary where there's like one adversary that sees everything. So think about like DDH or RSA or any standard assumption cryptography that you can think of. Okay, so let me go to the applications. So there's two applications I wanted to talk about, one about proofs of replicated storage and one about Biki cryptography. So the proofs of replicated storage as the following question. So let's say I want to have a backup of Wikipedia on the cloud. And I want to use some cloud service to store backups of Wikipedia. And the cloud service promises to do replication, to store many copies of this data, not just one. So if one server like breaks down, we can still recover. And I want to somehow audit the cloud and make sure that it's not lying to me, that it is actually storing many copies of this data. So one thing I can do is just periodically download the data from the cloud and let's say verify some hash of the data that I store locally. And that would be an audit that it's actually storing the data. It turns out I can do something a little better called proofs of retrievability that let me do this with a much more efficient audit protocol where I don't have to download the entire data. But let me ignore what proofs of retrievability are, or even this efficiency property. The problem with this approach is, so I'm going to try to like make sure the cloud is storing the Wikipedia data, but what if the cloud is only storing one copy? And it can pretend it's storing many copies no matter what audit I design, right? It has the data. There's no way for me to check that it's storing one copy versus two copy. In fact, what if the cloud is even not storing any copies and using the fact that Wikipedia is also like stored on, there's another place on the internet where it's publicly available. So it's not storing any backup copies at all. So how can I actually ensure that the cloud is storing many backup copies of Wikipedia? And the idea is that I'm going to not ask the cloud to store Wikipedia itself, but rather to store various incompressible encodings of the Wikipedia data. So here I'm encoding the Wikipedia several times, 4 times, or as many times as the cloud is saying, as many replicas as the cloud promises to have. And I get these different code words that are different representation of Wikipedia. So I get a red code word, green code word, yellow code word, and purple code word. And the idea is if I use an incompressible encoding to do this, then I'll use an incompressible encoding to do this and then run an audit that checks that the cloud has all these different code words. And the main property that I ensure is that the cloud cannot save on space in any way while being able to pass the audit. So the cloud really has to store 4 different versions of Wikipedia in order to be able to pass this audit. It cannot compress down these 4 code words below the size of 4 times the size of the Wikipedia data. So, so I want to say, like, you don't actually ensure that the cloud is storing like 4 copies on 4 different servers in 4 different places. They might all be on the same server, etc. But at least it shows, it guarantees that the cloud cannot just like save on space and cheat by saving on space. Okay, so that's the first application. That's from this work of Damgård, Ganesh and Orlandi. I want to mention that for this application, you need the composability property. The second application I want to spend a little more time on is from our paper, and it's an application for Biki cryptography.
Daniel, quick question about composition. Is the CRS as long as all of the code words?
That's right. So in the CRS model, you would need a huge CRS that's as big as all the code words. In the random oracle model, you get around that.
I see. Okay. Okay. Thanks.
Yeah.
So I guess just to build off that, because I was thinking the same thing. So if you don't have a random oracle, then this application is like a little hand wavy, because you need to somehow be able to have access to the CRS, which kind of either you're holding the CRS locally, at which point you could just like hold the entire database locally, or you need to trust the cloud to hold the CRS for you, and it kind of, you get into a little bit of a sketchy situation, but random oracle just makes that go away and makes this very useful, right?
I agree, yeah.
Okay,
yeah,
cool, just making sure.
Yeah, definitely the fact that in the CRS model, you need this huge CRS is a big downside. And yeah, unfortunately, we show that's necessary if you for black box proofs of security. Okay, so let me talk about the second application to Biki cryptography. And so this is a topic that there's been a lot of prior work. It's an area that's motivated by the issue that computers can become compromised. So, you know, a hacker, some remote attacker can cause you to download some malware or hack into your system. And if an attacker does that, probably the first thing they're going to do is steal any secret keys, any cryptographic secret keys that you have on the system. So you should think of secret keys stored in the system as being like high value gems that are probably the first thing the adversary is going to steal out of a compromised system. And once cryptographic keys are exfiltrated, any security that they were meant to provide is lost. So this is like a really bad way to break cryptographic security. And so an idea to protect against that is let's make secret keys big, like on the order of many gigabytes or even terabytes. And the idea is that a big secret key, let's say 50 gigabyte secret key, is harder to exfiltrate than like a 128 or 256-bit AES key. And so there might be several reasons why it's harder to exfiltrate. Maybe your system has some system security that actually would detect large amounts of leakage, like if many gigabytes are leaking, it shouldn't be. You might have some firewall or some system security that would detect that. Or just the attacker doesn't have enough time while he's undetected on the system to download a huge amount of data. Or it might just like be too costly to do these attacks to download 50 gigabytes each time you want to steal someone's secret key. And so like doing it on a mass scale would not be profitable for the adversary. Okay, and so I just want to use an analogy that's due to Adi Shamir. So he actually suggested doing something like this. And his analogy was, well, if you have a small secret key, it's like a gem. Gems are really easy to steal. You need a lot of security to protect like valuable gemstones. Statue of Liberty is also a pretty valuable object, but you don't need a lot of security to protect the Statue of Liberty. It's pretty hard to steal a Statue of Liberty. So that's the idea. Let's make our secret keys like the Statue of Liberty, huge things that are hard to steal rather than little gemstones that are really easy to steal. So this is the motivation behind Biki cryptography, also known as bounded retrieval model. And there's been a number of works that have studied the setting. Essentially, there's two goals in this setting. So the goal one is to come up with schemes that are very leakage resilient. So security holds even if the adversary exfiltrates a large amount of data about the secret key, but not the whole secret key. So if the amount of data that leaks out of the system is, let's say, 99% the size of the secret key, you should still have security. And the second goal is I should be able to make my secret key as big as I want, as huge as I want, many gigabytes, many terabytes, but still the efficiency of the crypto system should be preserved. So even though the secret key is huge, the crypto system should be very efficient. In particular, it means the adversary can't even, the scheme, the cryptographic scheme, can't even read the entire secret key to do each operation, because that would already be too inefficient to read a terabyte long key. So we want some nice locality where every time you do a cryptographic operation, the scheme only reads a few bits, some small number of bits of the secret key. So there's been a lot of work constructing these types of crypto systems. We know how to do public encryption and authentication, etc. But one common problem to all of these crypto systems is that they require the user to waste a huge amount of their hard drive space, of their storage, storing some useless secret key that is only useful for cryptography. So we're telling the user to spend gigabytes or terabytes of their storage just for cryptography, and users might not like that. And so the new idea in this work is let's not do that. Let's actually make the key useful. Let's take data that the user would store anyway. Maybe let's say the user is storing an offline copy of Wikipedia for their own use. Let's tell them to use that as the secret key. So let's use Wikipedia as a secret key. Well, is Wikipedia a good secret key? No, that's a terrible idea, right? Wikipedia is public, it's online, everyone knows it. It's not secret, it's a terrible idea to use it as a secret key. So that's not what we're suggesting. Instead, we're saying use an incompressible encoding of Wikipedia as the secret key. And now you can see at least there's some merit in this idea. So at least, first of all, the incompressible encoding is somehow randomized. So there's some randomness, even if you know Wikipedia, you don't know the incompressible encoding. And moreover, it's hard for an adversary to exfiltrate the entire secret key without downloading too much data out of the compromised system, because that would mean that he can compress this incompressible encoding of Wikipedia. So, so this at least shows that it's hard for an adversary to just steal the secret key fully. It's still not clear whether you can use this to build a crypto system like public key encryption that's secure when the secret key is a incompressible encoding of Wikipedia, but we show how to do this. We show how to build public key encryption in this setting. So Sarah, how much time do I have?
You can keep going for probably, let's call it 8 more minutes. Does that work for everyone? We could also stop a little earlier in like 3 minutes and then talk about Ron's question in the chat.
But yeah.
Perfect. Let me take a few minutes to describe this public key encryption scheme. Hopefully I'll do it in 4 or 5 minutes.
Let's keep my question to questions. Yeah.
Okay. So the goal here is we want to design a public key encryption that's secure in this setting if the secret key of it is this incompressible encoding of some public data like Wikipedia. So I'll call this an encoding friendly Biki public key encryption. So the functionality says that I should be able to use any string as a secret key of this encryption scheme, because I want to use, let's say, some incompressible encoding of Wikipedia. And then the scheme should generate the corresponding public key once I give it the secret key that I want to use. The security says that security should hold as long as for any incompressible secret key. So even if the adversary gets like 99% leakage on the secret key, if the secret key is incompressible to start with, then the adversary should not be able to break the security of the system. And the efficiency is the same as standard Biki public key encryption. So the size of the public key, the encryption time, and decryption time should all be small. So there's a few challenges if you look at previous Biki crypto systems. So one challenge is in previous Biki crypto systems, the scheme generated its public key and secret key together. The secret key had a lot of structure, but now we want to just use any old thing as a secret key and any string as a secret key. So, so we cannot use the previous schemes as is. And the other challenge is that previous Biki schemes only guarantee security when the secret key is randomly generated via the keygen algorithm. Here I want security to hold even when the secret key doesn't have a lot of entropy, just some incompressible encoding. So just as long as the secret key is incompressible rather than uniformly random. So we need to design a new public key encryption scheme in this setting. And we do this using something called laconic OT. So maybe I'll just go pretty quickly through this. It's a pretty heavy hammer. Here's what laconic OT is. It allows some receiver Alice to take a long string, some big database, and hash it down to a small digest. and she'll send the digest over to some sender Bob. And now the sender Bob can pick any index of the string that Alice hashed, the ith bit of the database D that Alice hashed, and essentially encrypt two messages M0 and M1 such that Alice gets the message that depends, if the ith bit is a 0, she gets M0, if the ith bit is 1, she gets M1. So somehow he computes the ciphertext E that encrypts M0 and M1, and he sends the index and this message E, the ciphertext E, to Alice, and Alice is able to recover the message that corresponds to ith bit of the database. So it's like Alice here has many, many OT queries for many different bits for this whole database D that she sends all together using one small digest. And the main properties are, so first of all, the sender shouldn't learn anything about the database from the digest. It should be some sort of randomized hash, maybe more like a commitment. And also the receiver shouldn't learn anything about the bit that she's not qualified to decrypt, the bit that doesn't, that's the opposite one of what her data is. And the efficiency is the digest is small and the runtime of the send and receive algorithms are all small, only polylogarithmic in the database size. So we have constructions of this laconic OT under a lot of nice public key assumptions like DDH, LWE, etc. It's a pretty heavy hammer though. These constructions are not very efficient in real life. So assumptions-wise, it's a nice primitive, but practicality-wise, not so nice. So let me just show you quickly how to use this to construct Biki public key encryption. So the public key is just going to be this digest of a secret key. So I was going to take the secret key, which is this incompressible encoding, let's say, of some data she's storing, like Wikipedia. It's going to hash it down, and the public key is going to be the digest of this laconic OT. And now when Bob wants to encrypt a message M to her, he does two things. He's going to first secret share the message into D shares, where D is some parameter, but think of it like security parameters, something relatively small relative to the size of the secret key. And then he's going to pick a random subset of locations in Alice's secret key and use them to send the corresponding shares. So he's going to actually encrypt the shares of the message. And you should think of the semantics of this saying, if the ith bit of the database is a 0, you're going to recover the jth share. And if the ith bit is a 1, you'll also recover the jth share. But so he's putting the jth share in both positions. But in one case, you'll recover like the orange version of the jth share. In the other case, you'll recover the yellow version. So he's putting the jth share in both positions. It doesn't matter what bit Alice has, she'll recover the jth share. And so you can see correctness. So Alice can use the fact that she knows the secret key to decrypt the ciphertext E sub j and recover all the shares of the message and therefore get the entire message. But I want to say that this also ensures that Alice has to know the entire secret key, or the adversary has to know the entire secret key to decrypt. And I don't think I have enough time to do a formal proof, so I'm just gonna, I'm just gonna give you very high level intuition. And the idea is that if the adversary doesn't know the index, the ith index of the database, or one of the indices that I select, one of the D indices that Bob selects when he encrypts, then he's not sure if that location is a 0 or 1. And that means that he's not sure which of the two copies of the message, the orange one or the yellow one, he's allowed to decrypt. But that can't be, because if we change the orange one to like an encryption of junk, or we change the yellow one to an encryption of junk, in one of the two cases, the adversary is unable to decrypt. So somehow he has to know which of the two cases would make him be unable to decrypt. And depending on that, we can actually extract out the location of the secret key that the adversary has to know when he's decrypting this ciphertext. Okay, so essentially he has to know what the bit is in that location, because if I modify the ciphertext to 0 out to remove one of the two shares, either the orange or yellow one, he'll need to stop working in one of the two cases. And by checking which of the two cases he stops working, I know what the ith bit of the I can extract out what the ith bit of the secret key is. So I had a slide that did that in more detail, but I'm going to just skip over that. So let me just end very quickly with a few open questions. So the first open question is, are public key assumptions necessary for incompressible encoding? So right now we need trapdoor permutations, or in fact some special types of trapdoor permutations. Can you do this using just mini-crypt assumptions? And I suspect the answer is no. So one interesting question is to show impossibility and that you cannot build incompressible encodings just in the random oracle model. So like an Impaliazzo-Rodich style impossibility result. It'd be also interesting for practicality to construct schemes that just minimize the number of public key operations. Right now, the number of public key operations is linear in the data size. Altogether, better practical constructions of incompressible encodings, also of encoding-friendly Biki crypto systems. So right now we're using Laconic LT. It's a pretty heavy hammer. Can you make this more efficient? And lastly, just more applications of incompressible encoding. I think it's a very interesting primitive, and I'm hoping that there's really other places in crypto where this could be useful. So let me stop here. Thank you.
Okay, cool. Are there any other questions before we get to Ron's question from the chat from a while ago?
So what is the parameter D? I mean, is it order of the security parameter?
Yeah, that's right. Just security parameters enough.
Okay.
So have you thought about encoding friendly other primitives like proof of space protocols, for example?
Oh, I didn't think about proof of space. So
that would be,
more like,
be cool to be able to, have people store useful data instead of random graphs. You haven't thought about it?
I have not thought about it. I thought there was actually some work by Krzysztof that did something similar, but I don't know. I'm not sure.
Yeah.
So,
All right, Ron's question from the chat.
yeah, so I don't know if Daniel, there must be some misunderstanding something basic here. Actually, I was looking at the paper and I'm looking at the definition, but right. So you want the encoding should be expanding, right?
Well, not too expanding. So, but yeah, it needs to at least store the data.
Right. So. Right. So if you
so the version I'm looking at what you wrote, and is it the very first chat message?
Yeah, exactly. Yeah. So it should
be. That's so is R small or big?
So I want R to be bigger than M, right?
So Ron, I think this is the trivial construction essentially. However big R is, that's the amount of incompressibility you get. The second part you can trivially compress because you know, right? If you remember R and you know M, you can come up with O of R plus M. So essentially, this is the trivial construction where if you add beta bits of randomness, you'll make sure you can't compress below beta bits. But like, think about it this way. Let's say my message size is 1 terabyte. So if I want to have an encoding that doesn't have too much overhead, like I want to have a 1.1 terabyte size encoding. So if you do that, you'll make R 0.1 terabytes, okay. And then your incompressible will be just 0.1 terabytes, not 1.1.
Okay, now I got it. Okay, no, I got it. Okay, so that's why all this all or nothing transforms, etc., that don't work because they expand a lot. This concept of all or nothing transforms also what bothered me, from that they expand a lot. That's right.
That's right. Yeah. Yeah, I think none of them, they don't, well, we know information theoretically cannot beat the trivial scheme, like the one where if you want to get incompressibility by beta bits, you just append beta bits of randomness.
Right, no, but there are kind of or nothing transforms, computational ones. But I think Right. The point is that they expand by quite a bit.
I think it's physical bits leakage. So in AUNT, you allowed only physical bits leakage, and here you can do whatever you want. You can look at the code word and then get the seed out. So this will not work. AUNT is only secure for physical leakage.
I see.
So it restricts the attacker to compress to physical bit leakage and not to something more complicated.
Okay.
Right, the attacker doesn't see the whole code word. He only sees a few positions of the code word, or few bits.
So when you translate this attack, it kind of means that maybe he looks at the whole file, but he simply only will choose a small subset of bits. He's not smart enough to do some better decompression.
Right, okay.
Daniel?
Uh-huh.
Is there an outstanding question, or can I ask a question?
Yeah.
I wanted to ask, I'm Googling. There's this work called Public Incompressible Encodings by some people, Cornell Tech, and Ben Fish at Stanford. Do you know about this work? I was just going to ask how it's related or different, or if they're just different.
Good. I think there's been work.
If it'll make your life easier.
There has been some work on a similar primitive for things like proofs of replicated storage. In that context, they did. And I think essentially the difference is they don't consider like arbitrary polynomial time adversaries. They say that if the adversary runs in like essentially the adversary can compress, but to do so would require like quadratic or cubic time or something, rather than rather than that it's impossible in arbitrary polynomial time.
Got it.
I may not be remembering that quite correctly, but there's some it's something along those lines.
Okay, thanks.
Okay, I think we're officially over time.
Okay.
So
That's great.
it was lovely.
Okay.
Great, thanks very much.